So what'd you get for this final example, example 10 here? Did you get 1? Did you get 0? Did you get pi or something like that? If you did, you're wrong. So let's see what you may have done right, what you may have done wrong. I don't know. Let's see. We want to take the limit. First thing to do is just go ahead and do some direct substitution in here. So if I plug in our 0, get 1 plus the sine of 0. See, what is this? Sine of 0, okay, raised to the cotangent of 0 power. So the sine of 0 is 0, so I just get 1 on that part. Let's throw some arrows in here for some reason. And then the cotangent of 0. Cotangent of 0 is, I think there's an asymptote there. Okay, let's badoop here. Because on tangent, it's equal to 0, right? So I'm pretty sure there's an asymptote here. Cotangent is equal to cosine over sine, and at 0, that's 1, 0. So it's 1 divided by 0. So yeah, you did get in infinity here. And it's from the right-hand side, so you should get a positive infinity. So this is not L'Hopitalable, so what we do have to do, since it is an indeterminate power, is that we're going to have to set this up as a logarithmic differentiation. Let's set this thing equal to y. The limit as x approaches 0 from the right of 1 plus 4, well, no, sine 4x, I think. And then a cotangent of x. Right? Right. Okay. And then we're going to take the natural log of both sides. The natural log of y is equal to, natural log is just going to pass through this. And we have the natural log of 1 plus sine of 4x, cotangent of x. And let's not leapfrog, but just use the property of exponents, which brings that cotangent down. Cot x times, oh, don't forget the natural log part of it, 1 plus the sine of 4x. Okay, so we already said that the cotangent of x is equal to an infinity. So this part is infinity. And then we had a 1 for the inside of this, so we have the natural log of 1, which is 0. Now I have the indeterminate product. Indeterminate product, I have to turn into a quotient. I'm going to bring one of these guys down to the bottom. And my suggestion, of course, is to bring your cotangent down to the bottom. Not this. That's going to be a disaster. Disaster waiting to happen. Netflix, if you are listening, don't go for that one as your next limited series as like some disaster pick, you know, because some people like those kind of disaster movies. That it wouldn't be interesting. Nobody would watch it. But the whole L'Hopital and Bernoulli thing, yeah, people would watch it. This is my pitch for it. Make sure you give me credit. I don't need any money. I just want credit on it. You know, some sort of, I don't know, maybe make me an executive producer. I don't even know what those people do, but just put my name on it. It'll be fine. All right, so we're going to put natural log 1 plus the sine of 4x over the, no, that's incorrect, 1 over cotangent of x. Hey, you know, 1 over cotangent of x, that's equal to the tangent of x. So I am going to just rewrite that again as tangent of x. Very convenient. And now let's plug 0 in again. So let's verify we do, in fact, get, you know, an indeterminate form. So the sine of 4x, that's 0 plus 1. Natural log of 1 is equal to 0. So I've got a 0 on the top, and the tangent of 0 is equal to 0. Yay, finally, it's L'Hopitalable. So let's take the derivative of the top and the bottom, avoiding the quotient rule like crazy, because that's not what we're doing here. And hopefully, after doing this quite a few times, when you have to use the quotient rule, you don't revert to, you know, this derivative of the top and derivative of the bottom thing, because then you can get that wrong. All right, so now the derivative of the natural log of 1 plus the sine of 4x is a u prime over u. So the derivative of 1 plus sine of 4x is 4 cosine of 4x. Derivative of the 1 is going to be 0. Derivative of sine of 4x is cosine of 4x. And then 4x is an interior function, so you have to use the chain rule on it. And its derivative is 4 over 1 plus the sine of 4x. And now take the derivative of the denominator. What's the derivative of tangent? It is secant squared x. So far, so good. All right, now we want to try our direct substitution once again. Let's see if we have to use L'Hopital's again or if we're good to go. All right, let's change colors. So on the top, I have the cosine of 4 times 0. So it's cosine of 0, that's 1. So 4 times 1 is 4 over 1 plus the sine of 4 times 0. We already said that that's equal to 0. Nice. Over the secant squared of 0. All right, so that one I may have to do over here on the margin. Think of it instead of, first of all, the secant of 0, which is equal to 1 over cosine of 0. And then cosine of 0, we already know is 1. So this is 1 over 1, which is 1, and we're going to square it, which is equal to 1. So I get 4 over 1, which is 4, over 1, which is equal to 4. Wow, okay. Lots of stuff happening right here. Is our final answer equal to 4? No, it is not. Remember, that is equal to the natural log of y. So the natural log of y is equal to 4, exponentiate here, and we get y, which is equal to our limit. X goes to 0 from the right? Yeah, okay. Of whatever that thing was, 1 plus the sine of 4x to the cotangent. That's what this is supposed to say. Come on, Apple Pencil, of x is equal to e to the 4th power. Boop, some sort of compromise in that numerical tug of war. All right, so let's recap before we end this glorious lesson here with a summary here. So here are some determinate forms. You do not use L'Hopital's rule on these determinate forms. You just do some sort of direct substitution. If you have infinity plus infinity, not indeterminate, it's just more infinity, okay? Negative infinity minus another infinity, it's still more negative infinity. It is completely determinate. 0 to the infinite power is not indeterminate. It's still 0. Okay, it's the reverse of that one, which is indeterminate. Okay, and then same thing here, 0 to the negative infinity as a power is equal to infinity. Once again, it's the reverse of those, or I should say that these two things being switched here, that is when we get an indeterminate form. It's kind of like this. 0 over 1 is a determinate form, but 1 over 0 is still determinate, but it's undefined, right? So kind of think of it in that kind of way. All right, and then finally, our indeterminate forms, we have our friends, which are L'Hopitalable. It's 0 over 0 or infinity over infinity, and there could be some negative signs thrown in there. We want to use L'Hopital's rule. And here are our new ones. We've got 0 times infinity. That's your product. To get rid of that, to turn it into something that's L'Hopitalable, you're just going to bring one of those functions down to the bottom. You're going to turn it into a quotient. Okay, then we have infinity minus infinity. That's the one that looks like a cat face. If you're into cats. If you're not into cats, maybe it looks like some other kind of animal that you are into. Anyway, infinity minus infinity, you still need to write that as a quotient. You may have to get a common denominator. You may have to try to rationalize. You got to do something to turn it into a quotient. And then finally, we have our indeterminate products, which we are going to use logarithmic kind of differentiation here. We're just going to take log of both sides, and that's going to bring the exponent down in a very convenient way. It's probably going to turn it into something like this, which you're going to have to rewrite as a quotient. Once you do, now you have your 0 over 0 or your infinity over infinity, and you can use your L'Hopital's rule. There you go. There's your L'Hopital's rule in a nutshell. Okay, so when discovering an indeterminate form, avoid using an equal sign. Remember, on the AP exam, if you use an equal sign here, you're going to lose your points here. And if you're being totally thorough, you do your top and your bottom completely separately. Say, oh, look, the limit of the top, it's equal to 0. The limit of the bottom is equal to 0. So by L'Hopital's rule, here's the limit, and then you take the derivatives of the top and the bottom. Okay, so don't lose some precious AP points for bad notation and stuff. Okay, there you go, L'Hopital's rule. And you know what? Just because I'm feeling very gracious here, I'm probably going to throw in a supplement here. I'm going to give you some sort of free response question because I want you to have this exposure to using L'Hopital's rule and making sure that you are paying attention to your notation for those AP graders. And look at this. What's going on here? It's a double page. And just in case you're wondering here, EOO is every other odd. Ta-da!